So in the Bohr model of a single electron atom, an electron moves along circular orbits around a nucleus that has mass of mp. So right now we have a nucleus. In the center there is a proton who has mass of mp, and there is this it has also a charge of positive, obviously, because protons are positively charged, and the electron is moving in a circular orbit around this proton in the center. And here we have in figure 1 3 discrete energy states, basically, and also their corresponding energies. So the N1 is called the ground state. It tends to be the most negative of the three. Okay, you guys know how this works, right? To go up, you have to absorb a photon, and to go down, you have to release a photon, which means release light, most likely. Okay, now A draw arrows on figure 1 to represent all the possible atomic transitions between the states shown that could result in the emission of a photon. To emit a photon, the electron has to drop from a higher level to a lower level. So if we drop from here to here, that would do it. If we drop from here to here, that would do it. And if we drop from here to here, that would also do it. 3 possible transitions, basically. Okay. Yeah. Okay, B, the electron orbits the nucleus at radius of r1 when the atom is in n1 state. Derive an expression for the total energy of the atom when the atom is in the n1 state. Express your answer in terms of the charge, r1, and any physical constants as appropriate. Begin your derivation by writing the fundamental physics principle or an equation from the reference information. Okay, so have you guys heard of something called the conservation of energy? What do you know about that conservation of energy? Let me guess, energy is conserved? Is that what you... Okay. Any comment? How is the cat?
She's good.
Okay. So we're going to say total energy, which is E1, is equal to 2 things: potential energy and kinetic energy. So U plus K. Okay. Do you guys know the equation of the potential energy from your equation sheet? Electrical potential energy, I mean. K Q1 Q2 over R. Okay. And equation for the K is equal to half mv squared. So far so good. Now right now let's replace. So we're going to say E1 is equal to K. Now instead of Q1 and Q2, can we just write, because I said E, so instead of K, a Q, put E, right? We're discussing electron orbiting a proton. That means E times E over R, okay? But as we know, electrons are negative, right? So negative times positive is negative. So we're going to say E1 is equal to negative. And instead of K, you should put half ME V squared. E times E is going to be E squared. And the radius is going to be R1. So now we took care of the E. We gave them E. We gave them R1. We gave them physical constant, okay, which is the K. But we're still running into issues because they said, only these symbols. Right now I have to take care of the ME and also of the V. They got to be removed somehow. So the electron is moving in a circular motion, correct? That means that we could say quite nicely that the electric force it's experiencing is equal to the centripetal force, which is causing it to move in a circular motion. Now the equation for centripetal force is going to be m v squared over r. And the electric force is going to be k q1 q2 over r1 squared. But the force has an absolute value on it. So even if the charge is negative, it becomes ultimately positive. Okay, now we're going to just make that into e squared. And I'm going to say that v squared is equal to me times r1 squared r1 times k times e squared. And you can now cancel an r1 with a square. So we're going to say v squared is equal to k e squared over me times r1. And now I could say e1 is equal to negative k e squared r1 plus half, and also me. And instead of v squared, you put k e squared over me times r1. Cancel the me's. So we're going to get e1 is equal to negative k e squared over r1 plus half k e squared over r1. And of course I could now combine them because they both have the same denominator, which is the r1. So it's like saying minus 1 plus half, which is equal to minus half k e squared r1. Okay. Very good.
Mister, I'm still confused as to why we didn't number the e's in the very beginning.
Wait, now what?
We didn't number the e's.
They don't want any numbers. They want you to keep it in terms of e. So don't say 1.6 times, Don't say that. They don't want that. Okay. That was part B for derive. C. In the classical model of the atom, it was assumed that an electron could orbit the nucleus at any radius. On figure 2, based on the classical model, sketch the total energy of the atom as a function of r. Okay, so now don't forget that our equation is going to be E is equal to negative half k e squared over r1. Okay. Now, is our energy going to be positive or negative? Negative. Because of the negative sign, right? So you have to draw it here. You have to draw it under the x-axis. Okay, now, tell me, if the r1 is 0, how much will the energy be? You're dividing by 0, right? So what do you get?
0.
No.
You don't need to say
You're taking calculus. You better not say that. You're dividing by 0, so what do you get?
so a number over a 0.
Mm-hmm.
You get the number.
No, isn't it like
It's a 0.
well, it's a number over 0, and that can't happen.
Could. We get infinity,
Oh my god.
but negative infinity.
Oh yeah, that's right.
I think we're cooked. Okay, so
Let me know that for
okay, so like this. Okay? In the beginning, right?
Yeah.
But then as the R1 gets larger, so your denominator gets larger, what happens to your value of E?
It decreases.
It decreases, right? But again, it's negative. So as the R gets bigger, the E becomes closer to 0. Yeah. Are we cooked or
Not yet.
still have time? Okay. D. Consider the Bohr model of the atom and the states shown in figure 1. The electron orbits the nucleus at radii R2 and R3 when the atom is in the N2 and the N3 states respectively. Indicate whether R1 is greater than, less than, or equal to R2. Briefly justify your answer by using the representation. Okay, so they're saying, let me ask you a question actually about this equation. So E is equal to negative half K E squared over R1. Okay, so if the R is larger, what happens to the E?
It decreases.
How? If the R1 is larger, does the E become less negative or more negative?
More negative.
Less negative. Shall I explain to you why? Okay. So look, imagine if you have 1 over 8 minus versus 1 over 16. So which one is the bigger number here?
Negative
Not again.
Yeah.
1 over 8.
This one.
Yeah.
Because negative, everything is the opposite.
Yeah, it's all
Oh, right.
Yeah. So this is the bigger number. Okay? And so basically, as the R gets bigger, the E becomes less negative. Yeah. And so R3 is going to be bigger than R2. Okay? Obviously, we're going to get farther from the nucleus. The radius has to get also bigger. And and as the R increases, the E becomes less negative, so the E becomes larger according to the equation. Negative half K E squared over R1. Okay, so which one is going to have more energy? At the third radius or the second radius? Third being bigger, radius wise. So energy at third radius is more than energy at the second radius. Because as we said, R3 is bigger than R2. And the bigger the R, the E becomes less negative, right? Let's just do some math here. Choose a number, please.
2.
Okay. Choose another number.
4.
So which one here is bigger?
The 4.
The 1 over 4. The negative. Because it's less negative. Okay. So when the bottom increases, the whole thing will also increase. Because of the negative sign affecting how things work, basically. Good? Yeah.